Okay, so what I demonstrated in class was that if I raise a piece of chalk, say from here to here, and then drop it back to the original point, gravity has done work on the chalk as I raised it and then again as I lowered it. When I raised the chalk, the displacement was in this direction and the gravitational force is in this direction, so gravity did negative work on the chalk. And if I toss the chalk up to that height, gravity does negative work on it, which is why it eventually comes to rest before it starts falling back down. Now, as the chalk falls, gravity does positive work on it because displacement is now downward and the gravitational force is downward. So our F grav times delta S is going to give us a positive result. When I raise the chalk, then by virtue of having been raised, it has energy available to it through the action of gravity to fall back to its original position and increase its kinetic energy accordingly. So that in raising, gravity does negative work, which means that the potential energy change will be positive. Potential energy increases, and whatever the increase in potential energy is, gravity, when it acts in the opposite direction, is going to do work equal to the magnitude of the increase in potential energy, to the potential energy increase we got going from here to here, and that's going to be equal to the magnitude of the potential energy decrease as we drop to the original position. So intuitively, I lift something, I increase its potential energy. I release it, potential energy decreases back to the original amount, and a decrease in potential energy because of this definition, or consistent with this definition, means positive work is being done on the object by gravity, and if there are no other forces acting, all the work done in raising the object will come back as kinetic energy when it's dropped back to its original position. Now you can read more about it. The text, of course, will define change in potential energy, and we'll define a conservative force, lost my train of thought for a minute, as a path-independent force. Okay. Or as a force that does zero work if you follow any path back to its original point. For our present purposes, that simply means if you raise something against gravity, then when it's lowered, the energy kind of comes back to you. Now there's a formula for gravitational potential energy, mgy or mgh. I really dislike that formula, and the reason I dislike it is people use it when it doesn't apply. If I stretch out a spring, an ideal spring, and a good metal spring is pretty close to ideal. If I stretch it out, I do work on it. If I release it, it snaps back, and we have an increase in kinetic energy that is ideally equal to the work I did on it. So an ideal elastic force is conservative. The forces it exerts in going from here to here are the same as the forces it exerts at equal positions as I go from here to here. The forces, from here to here are the same as the forces from here to here, which means the work from here to here is equal and opposite to the work from here to here. Okay. Now, an actual spring heats up a little bit when you stretch it, and you have hysteresis loop and all kinds of stuff that we don't need to talk about right now, that mean that actually the work you get going back isn't quite as great as the work you get, as the work you do when you stretch it out. Ideal spring, we regard that difference as negligible. Okay, so for a spring, you don't have any mgh or mgy, you have something completely different. You have a 1/2 kx squared, and we've already seen that. And we'll talk about that some more. Okay, electrostatic forces have similar properties in that if you do work on the thing this way and then release it, the energy comes back as it moves back to its original position. So, ideal spring forces are conservative. Electrostatic forces are conservative. And there are other examples of conservative forces, but for the moment, these will do. And again, part of my point is that MGH or MGY only works in very limited condition of your conservative force is gravitational, and you're close to the center of the Earth. You're close to the surface of the Earth. Or your distance from the surface of the Earth doesn't change, or your distance from the center of the Earth doesn't change significantly. Doesn't work if you're trying to put a satellite in geosynchronous orbit. I use the example. MGH or MGY will work okay if you're trying to calculate the amount of fuel you need to get a rocket into low Earth orbit. You also have to be able to get the kinetic energy up there, but that's another easy calculation. It doesn't work if you're trying to go to geosynchronous orbit. Between surface of the Earth and low Earth orbit, your gravitational forces don't change all that much. So G stays pretty much the same. Going out to a geosynchronous orbit, your gravitational forces decrease by factors of tens. They decrease drastically. So if you try to load enough fuel to get the rocket to geosynchronous orbit using MGH, your rocket's never going to get there because the fuel's going to be too heavy. It'll never make it. You'll never get it there. I'll never say never. There are other modes of propulsion that might do it, but not with solid or liquid rocket fuel. Not with the technology I think we have today. Now, I'm not a rocket scientist, but it seems pretty obvious. You would be packing many times the amount of fuel that you need, and the fuel is heavy. You'd never get it there. That's my prediction. Ask a rocket scientist or ask me to do more careful calculations because it's not that hard. That rocket science is. This calculation isn't. Okay. So with that idea, that's kind of an introduction to conservative forces and potential energy. In this case, we're going to apply it to gravitational forces, but we're still not going to use MGH. It's a bad habit. Even by the end of the year, I have people trying to use MGH for potential energy changes in a magnetic field. It doesn't work at all, and if you use it, you're just bypassing understanding of what things really mean. Okay, well, that's a little bit about conservative forces. The other thing is, and the thing that's important here is, whatever work is done by your gravitational force, we're going to assume is the kinetic energy change of this wheel. So how are you going to calculate the kinetic energy change of the wheel? Now that's not accurate because the wheel's got a lot of friction. I mean, I stood in the thing about there and it didn't move until I leaned. So it took, probably 1,000, that. We won't talk about what it took because we're trying to derive that whole idea. Okay, that's the energy situation here. Now I want to talk a little bit about the circular model for trig functions.